I'd like to welcome everyone this afternoon. I saw some people said they did not get the link this morning. I am surprised at that because I sent the link out since Thursday of last week. But anyone who does not have the link or know of someone, please let me know. It's always good. Send me an email and we will promptly respond. Thank you very much. I should remind you here that Suzanne has indicated that the exam dates for set around the 19th of March. She's going to send out a circular about the logistics, etc., because we know there's water distribution 1 and 2 and water treatment 1 and 2. So we're going to sort these out. Okay, so have a good day. All over to you, Mike.
Thanks, Ignatius. And actually, to all of you, use the chat and just let me know whether you're going to be writing a level 1 or a level 2 exam, just so I get a sense. The materials, there is quite a bit of overlap, and the math and the disinfection material tends to be the same. But yeah, it'd be good to have a sense of how many out of the, 9 of you that are in the group that are writing, potentially, what the sense is. Okay, I'm seeing 3 level 2s, that's good. And what we're gonna do, so just as I will be sending you at the end of the session, or probably Ignatius will, the answer sheet. I'll bring it up on the screen from last week on water sources. We'll just take a quick look at that, but I will forward that to you. Also a PDF of today's presentation, as well as the questions that are basically review questions for the week. And just to give you a heads up, basically this is week 5. So the way we've broken it out, we'll focus on wells and groundwater and wells today. We've done some work on the actual pumping out of groundwater and where groundwater sources, what factors lead to utilities choosing groundwater as a source. So we're going to focus on wells this week. Next week, a bit of water quality, and that includes sampling for bacteriological pathogens. And then we're going to move into the appurtenances of a water system. So looking at the types of hydrants, valves, water meters, and then pumps, electrical systems, SCADA systems, and so on. And then we'll move into review. And that really will basically take us to the end of the review period. And also, while we're looking at appurtenances, we will be looking also at some of the maintenance programs around them, because there's no sense having a bunch of fire hydrants or water meters if you as operators and the whole utility is unclear as to how to maintain them to basically get them to last as long as possible. The asset management piece is really around extending the useful life of an asset or a class of assets, and then taking together the whole water system. So thank you for everyone. We've got, looks like a pretty close to 50-50 split between 2s and 1s. So that's good. So we will, I'll try and emphasize where material will focus on, say, the higher level, but default, everything in this program will be covered, or potentially could be a question on a cert exam for level 1. So having said that, let's talk a little bit about wells. So this is kind of what we're looking at today. Exploring for groundwater, we've covered off a little bit. I want to show you a little bit about how it's regulated in BC, and I would love to hear on the chat from you about if your systems utilize groundwater, and if so, as opposed to surface water, and if so, do you have to do maintenance on wells, and what kind of wells are they? In fact, I found this video on YouTube, and it's very generic, but might be, I wouldn't mind getting your feedback on is this something that you're familiar with? This is only 30 seconds long, but basically all it says is water well drilling in the Caribbean. Narrative, it's just basically percussion-based drilling unit. Basically looking at actually installing the well. Pretty basic setup. We're going to talk a little bit more about how to happen. Different types of wells. See, basically this is the file. You don't really get a sense of how good it is already. But on the chat, let me know if this is something that you have in your system, if you're familiar with it. And if so, how many of you either work on, have participated in installation of wells? Was that anything at all familiar to you? So if it's not, just basically let me know that no, we don't have wells or we use surface water, something like that. But if you do, let me know. I'd love to hear. In BC, I'll give you a couple of examples of how groundwater is managed in BC. What we have is a, okay, so one response is no, we don't have surface water, it's basically groundwater. So there may be then, obviously, quite different maintenance practices for groundwater systems as surface water. As far as the exam goes, you've got to be comfortable with the terminology. I kind of have said it to operators here when you're studying for a certification exam, call it the refrigerator theory, that we basically, you are the refrigerator. We basically put a bunch of information into the fridge, and then on exam day, you open up the fridge and hopefully the information is still fresh. It hasn't gone bad. And that you can then pass your test. So with level 1 and to a large degree level 2, it's not so much analysis of concepts, but actually recognition and identification of components, identification of pathogens, identification of types of pathogens, identification of some of the treatment processes in a very basic way, because this is distribution, and then an identification and familiarity with the actual appurtenances, how they work, what their purpose is in a water system, and how we use them. And that will vary from place to place. Even here in BC, we have such a large geographic area that if you go basically almost 1,000 miles from the southern border of our province, where I am in Victoria, all the way up to the northern border with Yukon and Alaska. So you can imagine that the requirements around maintaining wells, maintaining reservoirs, and even things like how deep a water main is installed varies quite drastically. This part of the world, we'll talk some more about it, but a water main may only be 1 meter deep, 3 feet of cover. Whereas halfway up the province in Prince George, they're 12 feet deep and basically up to 14 to 16 feet deep. So, you know, when you're looking at almost 5 meters in depth, put a water main in the ground, it means that your maintenance practices are going to be different as a result. So thank you for those of you who let me know about your wells, and actually has more surface water systems than I had originally thought. So that's good. We'll look at a couple of examples of types of well construction and go from there. Great, so let's just go back to the PowerPoint. So we'll talk a little bit about groundwater in itself, how we build the well. For the exam, and this is really where the focus will be, is recognizing and identifying the different parts or components of a well, and also then some of the terminology around pumping water from wells. And we've covered off a little bit of that already, so that may be a bit of review, but that's good because that will be on the exam. And sanitary conditions really refers to protecting our customers from contamination. It's got nothing to do with connecting a well to wastewater. But when we talk about the sanitary installation and maintenance of a well, what we're really emphasizing is that when we pump water from that well, we have to ensure that the water itself is safe and that we don't do anything or let anything happen to the water as it comes out of the well. Because remember, when we were looking at surface water and impoundment of reservoirs, lakes, and then man-made reservoirs, we have to disinfect because that water is basically open to contamination by animals, by birds, aquatic life, and people if we use those reservoirs for recreational purposes. With groundwater, we have an advantage in the sense that the actual water itself is often, not always, but often safe from bacteriological, biological contamination. So that in many utilities, there's no disinfection when water is taken out of the ground. But that means we have to be extremely careful and diligent around protecting that water supply, because if we're not going to disinfect, if we're not going to add chlorine or hypochlorites of any kind to the water supply, then we have to make sure that as we're pulling water out of the ground, we don't contaminate it. So that's really what we're talking about with sanitary conditions. And we'll talk a little bit about maintenance of the wells also. Before you can put a well into operation, you got to find the water. So that means exploring for the groundwater. And various agencies, state or county or provincial in the case of Canada, actually manage the act of applying for a well, installing a well, testing the well, and then managing the relationship between existing wells. You can imagine in a community where there are multiple wells installed, many of them, in fact, all of them may have different amounts of yield. We'll talk about how much that is, how much can you pull safely out of groundwater without damaging the aquifer. Next person comes along, wants to install a well. Those agencies, one of their jobs is to ensure that the newcomer applying for a well permit, a permit to drill a well, and then to take water license out of the aquifer, isn't then going to have a detrimental or negative effect on the existing wells in the neighborhood. Because they're actually looking at where the water supply is the groundwater aquifer adequate enough for not only current use, but future use? And is it adequate on a year-round basis? When you have a seasonal change, we talked about a diurnal demand for water during the day, but you also have different demands throughout the year on a 12-month cycle. So how adequate is the water source and is the water supply? So usually in North America, engineers, geologists, geoscientists are engaged either managing the existing wells and assessing applications for new wells, or the actual on-site work that is done to install the well. So in terms of understanding what's happening, because all of our wells, some of the wells in BC may be 100 years old, some of them may be abandoned and capped off, but could potentially be reconnected to a customer supply. It's important to keep the date and maps of known and unknown wells, so that the people making decisions around permits for new well drilling have a good understanding of what is actually available in terms of, because we're talking about a shared resource, groundwater. As you know, when we looked at the cross-section of an aquifer, it doesn't stop at property boundaries. So there's private property and there's crown land or government land, public land, city land. Those aquifers move and water moves between them, those boundaries, irrespective of where someone's put a fence. So our investigations have to include all of the possible uses for that water. And that's typically done through licensing. Locations, when people are looking for wells, yeah, they'll look at surface features and they'll look at where surface water actually is. Does the surface water feature a creek or a stream? Does it exfiltrate or infiltrate? So in other words, are we pulling surface water, pulling from groundwater, or is it the other way around? Are those surface water features now allowing our aquifer to be recharged? Obviously, low spots tend to be better for groundwater, but not always. So just an example, this is actually the drawing on the left is the province of British Columbia. So this actually shows some of the wells in the Alaska Panhandle as well, but we map all of that through the province, through what's called the Ministry of Environment. In fact, I will share with you the in British Columbia, groundwater is actually managed through what's called the Ministry of Environment. And you can see there's whole sections for property owners about licensing, about dealing with droughts, water quality, and setting up a well and what regulations you have to follow. So there's quite a bit of detail. In fact, one of the detailed pieces right here is if you are a property owner, once you install it, you need to test it. So for well drillers and pump installers. So the government puts together guides for people that are going to be installing or then maintaining and running groundwater wells with good data that comes from both its own scientists and from the industry in general. The drawing on the right here, I'll just zoom it up a bit. You can see basically we did this in the hydraulics piece. A well casing has been installed, a pump is, the pump is turned on, and we actually see the drawdown in the aquifer. And that's measured. And then there's an observation well that is installed to actually monitor how much can we safely take from the groundwater. So it's quite a detailed process. We won't spend a lot of time on this because it's not necessarily on the exam. We've talked a little bit though in this about pumping rates, the cone of depression, and drawdown. So that we will cover off and review as well between now and the end of the program. But there's good data and information if you are installing a well and what you need to do as a good steward of the well itself so that you keep it safe and also that you don't draw more than you need to. So basically this guideline is how to know that you are even testing the well correctly. There's another little document here. Oh yeah, this is the one. So if you're a well owner in the province of BC, what do you need to know around protecting groundwater? So it tells the owner of the well what the law is and where that law is. It's under the Water Sustainability Act of the Ministry of Environment, but the regulation itself is the Groundwater Protection Regulation. It requires wells to be constructed properly, maintained, and then, if not needed anymore, safely decommissioned. Why it's important, obviously, It's not just about the safe removal of water for your customers, but it's also about protecting the groundwater itself. Make sure that you hire a proper registered well driller and pump installer, except for dug wells. And we're going to talk a little bit about the difference between, and this is on the exam, the difference between a dug well or a hand dug well and a borehole or a drilled well. So as this document says, a well less than 15 meters deep, right, is exempted, but otherwise the direct supervision of a registered well driller and or a professional hydrologist or geotechnical engineer. In other words, a qualified professional that will ensure that the work is done properly. And then that pumps are installed under the direct supervision of a professional. And so it goes on basically to say that here's some extra resources. Registered drillers in British Columbia are registered by and are connected to the Ministry of Environment. So they have to show to government, if they're ever asked or audited, that they are qualified to drill a well and that they're qualified to install a pump and that they can actually correctly quantify how much water the well is meant to pull out of the groundwater. Because you can imagine, if the groundwater is not managed correctly, then there's a problem with potential long-term viability of the resource. And I just wanted to show you this other, just the last thing. There's, as I say, tons of resources. So you can actually, if you have your ID number in the province of BC, these are all the wells. So anywhere in the province that is registered all through, and you can see it's a large province. Vancouver is this area. So you think, well, why are there so many wells? Oops. Why are there so many wells in Vancouver? But there are a lot used in agriculture. And along Vancouver Island, I live down here, but you can see it's a very large province as far as the requirements to manage groundwater. It's going to be very, very different. You know, along the coast, or the connection to the next door province is very high ground, the Rocky Mountains, versus a very dry central portion of the province, the Okanagan and the Caribou, and then a very wet area. So that the type of wells in these areas will vary based on the geology and the topography. And of course, based on municipalities allowing you to do that versus connecting to their water supply. But municipalities also manage these wells, right? There are a lot of supplies by cities and townships and villages around the province of BC that require wells and groundwater supply as opposed to surface water. And so therefore they are also underneath this legislation. So what you end up with in BC, and it's much the same across North America, and I'm assuming, and forgive me, I don't know your geography or the political setup for your utilities, but if you have wells, then they tend to be regulated by the central political authority, whether it's a regional government or an actual national government, some branch of that looks after water resources, and would assume, I assume, would do the same in terms of ensuring that wells, when they're installed, meet certain standards. And those standards would be established by scientists, hydrologists, geotechnical engineers, and so on. So it's all in aid of two things. One, can the water being pulled from the groundwater source, can it be managed over the long term so it's sustainable? And that means sustainable over, say, a 12-month period when you have fluctuations in temperature and in water use by your customers. And then the second part is, are the wells installed, drilled and installed and then maintained to a standard that prevents any waterborne disease? And that becomes really critical. Oops, we'll go back to this one. All right, we'll just carry on a little bit. So that's basically, in a nutshell, the how it's managed in BC. All right. So a couple of tests that happen. We do seismic tests, which is basically a shock wave sent into the ground, and that reveals the geology, the different types of rock and soil overburden, and if there are aquifers or spaces where groundwater can exist. So be familiar with the difference between a seismic test and a resistivity test. The ground, basically an electrical current that's sent through in the neighborhood of where a well is proposed. And of course, the old-fashioned way is basically digging a hole, a test hole or an exploration hole dug by hand or drilled to determine potential water volumes, because not every well that's drilled actually gets turned into a well. It may not prove adequate, or the water source may not actually exist where forecasters like geologists expect to find it. And so that means there are multiple times when the drill rig has to be moved to set up for a new location. So we'll talk a little bit about the types of construction techniques. And you should be familiar with basically the definitions between a hand dug well or a bored well, a driven well, which was very similar to the percussion one you saw in the video just now, and then the types of drilling itself, and the features, the general features that distinguish a hand dug well from a drilled well. I have a video that I would like to show you that basically explains that process. So let me see if I can set that one up for you. Actually, I found this other little video here. I'll share it with you. It's the second half of that first one about drilling in the Caribbean. You can see the portable generator basically set up there. Truck over on the right, one that held all the casing material, water supply. Unfortunately, this individual end stands exactly where they're putting the well. But you can see the percussion being used. So I'm going to send this video to you. Basically how wells are drilled and what we're looking for. And there will be a couple of questions that we'll talk about afterwards that may show up on the exam.
In this video, we're going to show you a little bit about what center state drilling does and why they're the best in the business. Dan McMahon is the owner and operator of Center State Drilling. It's a job that he's been doing for 30 years. Let's take a look at a job Dan did recently to show you how easy it is to get fresh, clean bore water when you know how. So the first and most crucial step is finding the very best place to drill.
Okay, basically what we're going to do here today is we're going to divine where the water is and find the location of two streams crossing one on top of the other. So what I'll do is turn around with a wire. I'm facing water and it dips. That's the edge of a stream there. And that's the middle of a stream going through there.
So I don't know if any of you've seen this, but this used to be the only way people found water underground, was usually with sticks that were cut into a Y fashion. But it's actually, people still divine water as opposed to using ground penetrating radar or seismic tests. the witchers, they call it water witching, but you can see, I'll just let them say it again. It's kind of cool.
Where the water is, and find the location of two streams crossing one on top of the other. So what I'll do is turn around with the wire. I'm facing water and it dips. That's the edge of the stream there. And that's the middle of the stream going through there. So now we want to find another one. And that's the edge of a stream there. And that's the middle. So they're both going to cross one over the top of the other, right about here. So that's where we're going to drill a hole and get lots and lots of water. If you just drill over there on one stream, that's all you're going to get is one stream, or over there, etc., etc. But if you come in here, you're going to get two streams from the one hole, which is going to give you the best result. I can drive a truck, I swear.
Now that we've worked out where the water is, the first step is to drill down through a couple of feet of topsoil, then down through what's called unconsolidated overburden, sand, gravel and clay. Next, Dan puts some large diameter casing down to create support so that when he hits water, it doesn't just wash out and collapse the ball.
So the water you may see coming out at the beginning is water that the driller has added to lubricate the actual drill assembly. They haven't hit water yet.
Then it's on to the real thing, drilling down to your water. For this, we use a hammer drill to get through the rock. For this job, Dan drilled through yellow sandstone, which is pretty soft. Then, at about 12 metres, he hit blue mudstone. Most jobs are completed in a day. This job took about 4 hours, which is pretty typical. But if we've got to go deeper, it can obviously take longer. We'll give you an estimate of the time when we come to give you a quote. So at 18 metres, that blue mudstone turned to blue sandstone, which is a harder rock and where we get our water. Because back in time when the earth here was pushed up by volcanic forces, the harder rock was the one that fractured. And it's these fractures that allow the underground water to actually flow through. So getting to that blue sandstone is the key to getting to your water.
So the other thing is that when you hire a professional water well driller, they will know the neighborhood, the features that typically exist where they intend to drill, because they'll have done that before over time for other customers or municipalities. Most municipalities don't hire or use their own internal. They will hire out a specialist well driller to do the work. And so they keep records of all of the wells they have drilled. And so they have a pretty good understanding of the depth, how far they have to go, and what kind of equipment they need to use, whether they're actually drilling through, in this case, sandstone and then clay, or if it's actual bedrock. And the well driller keeps those records, has those, of course, filed with the ministry and the relevant ministry or government agency. But they then become familiar and recognize the characteristics of the ground they're working in.
The next step is to put really good quality casing in. We slot the bottom length so that the water can get in along the whole length of the aquifer. We We put a seal above that to stop material falling down into the slots. And we cased the bore all the way to the bottom.
We used Australian-made casing, which is obviously more expensive than the cheap stuff that comes out of China and India, but it conforms to Australian standards. It's lead-free, it's made in Melbourne, and it's got a lifetime guarantee, and it supports Australian jobs. Cheap casing is made of quite inferior materials. It doesn't conform to Australian standards, and it's very, very brittle. It's quite thin. So in a lot of instances, that can collapse under hydrostatic pressure. If there's any movement in the ground, it can crush it, and then your pump's stuck in the hole. Your bore is basically useless. You've got to get someone in to pull all the casing out, if they can get it out, re-drill the bore, and then recase it with decent casing. So you've done your dough on the first hole, which you thought you might have been getting cheap, but it's not so cheap.
So basically what he's talking about is the type of material that in his part of the world, Australia, that they use. It's basically a C900 or PVC, which we'll talk about. There are different SDR, or basically rigidities of plastic pipe. Some can be used for pressurized water systems, others only for gravity systems, and similarly for well casing. So he's talking about using a more rigid type of casing, because if you can imagine the bore that has just happened, material can collapse and then put pressure against the casing. So he wanted to choose a material on the casing that is going to support and stand against any of the pressures that come from basically 18 meters below grade. And then what he'll do is put in a supporting grout between the existing ground and the casing. And then the pump will go down the middle of the casing to pull water out.
Do it properly the first time, or just don't do it.
Now we run an airline down the hole and we blow compressed air down the hole to blow the water out, which drags in any sediment and cuttings. We continue blowing the water out this way until the water runs clean. If you don't do this, dirty water will block and kill your pump.
Once the bore's clean, we shut the rig down, we pull the airline out, we grout the surface, and we've got a seal down below it so nothing can get in and block the water off. It's going to be safe from contamination. We've got a cap on top of the bore.
So you can imagine that, through the wet season, a lot of rain will fall and run across the ground there. So what he was talking about is a cap, and we'll show that on a cross section, either a well slab or a sanitary seal that stops surface water from running alongside, hitting where the well casing is, and then running down the outside of the casing, because then that gets into the aquifer, and then because he's drilled holes in the bottom of the casing, that then gets pumped out into our water system, and that could be pathogenic, right? So even though that groundwater is 18 meters below grade, and it's probably protected from any surface influence, the act of drilling down through it is now a potential source of contamination unless construction methods are done correctly.
As you see it now, it's all ready for the pump to be installed. So basically when we arrived, we've done the divining and we found out where there's two streams crossing one on top of the other. That's the best place to drill, because if there's enough water on the top stream, you stop there. You don't have to go down and pick up the second stream. But if there's not enough there, you've got the option of going down to the second stream. In this case, fortunately for the customer, there was plenty of water on the top stream, and that was at about 20 metres. We got into a good flow of that, and we ran it all the way down to the bottom of that stream, which was 24 metres. He's got around about 1,000, 1,200 gallons an hour, which is quite a lot of water. We offer a no water, no charge. Now, some other people do that as well, but if they get you 5 litres an hour, they say that's water, you're paying for it. I don't work like that. I'll guarantee you a usable amount of water, which in my opinion is at least 15 litres a minute. If I don't get water, I've done my dough, you're not happy, no one's happy, then I go and drill another hole somewhere else and see if we can find water there. But with the water divining, we get about a 95% success rate. And it's quite easy to pull up and say, well, where do you want the bore? We'll put it anywhere you want. But you could drill over here and have to go 80 metres, but if you drill here right on top of where the two streams are crossing, you've got all your water at 24 metres. So it's going to save you a lot of time and a lot of money and a lot of messing around. I've been doing this personally.
So he's talking about a well that will yield about 20 gallons per minute. So roughly US, let's assume those are US gallons, times 3.87 liters. So we're looking at almost 80 liters per minute. That's a good size production. Now, what we don't know is if in fact that's been approved in BC. That would have to be registered and confirmed through a yield test to make sure that that's a supply that can be done on a regular basis, that is adequate without having to put a tank. Because in an area where you may not get more water, what you'll see installed at the back end of that will be a tank or reservoir that can be filled over time so that the groundwater isn't overly taxed in the and draw that aquifer down too much.
For well over 30 years. My father started on the Snowy River scheme when they went through. That's where he got his introduction to drilling, and it's been a family business ever since. Just read the...
All right, so family business. So basically what he's saying is that, okay, we've been doing this a long time. So in other words, we know where to find water in your neighborhood. You have to tell us how much you need on a regular basis, and then we can determine whether our drill setup can provide that and whether the aquifer can support that. So that's not a bad little video about looking at how the well is drilled. But again, we're talking basically 24 meters was the total depth of that well. And so you're not digging that by hand. So that was an example of a drilled well. We'll look at a couple of other examples. So a dug well could be, in fact, just done by hand. Anywhere from 0.5 to 1.5 meters in diameter. So basically 18 inches to 5 feet in diameter, usually no greater than 10 meters. Hand dug wells in areas where the water table is high may only be 5 or 6 feet deep, maybe 2 meters deep together. And the other characteristic to remember about a dug well is that it's not going into bedrock. It's basically stopping at overburden. So you're not looking at having to break up hard rock in order for it to work. So typically where water table's high, here's an example of a dug well. Now this is more than 2 meters deep, but it's dug by hand, basically a shovel, into where the water table is. And you can see there's basically the means of getting the material out of the hole is a rope tied off to a bucket. So pretty basic, but very common. And some of these wells, you might see them lining them with brick. So hand dug, lining them with brick without grout, so that the water will, or without grout between every seam, so that water can percolate through the edge of the brick and fill up the well. And then basically it's just a hand process to pull water from the well. It's interesting, when I was in Africa 20 years ago in Malawi, the well of choice, was, or the most basic well, was a hand dug well, very similar to this, but brick lined, if they were lucky, square, lined with brick. And basically people took turns lifting water out of the well. A more advanced and very common, you might have wells like this. In fact, if you've seen them, let me know on chat. It's called an Africa Dev, so Africa Development well. And you can see it's basically 3 parts. Sometimes they're drilled, but sometimes they're hand dug and lined with concrete, like manhole sections that you would see in the sewer department. And then a slab around that allows for splash. People would put their buckets and vessels on the stand here, and then this little tray would trough would drain the excess water away so that it didn't turn everything into mud all around it. And when I was in Africa, in Malawi, it was basically, this was an improvement over that and allowed for, as you can imagine, a much more sanitary setup for taking water out of the ground. It wasn't very deep. These ones were maybe 20 feet deep. The hand dug wells that I worked on in Africa were about 2 meters deep, so 6 to 7 feet deep. And the water table's high. In that area of Malawi, there's a very tall escarpment, so there's a lot of runoff that comes down and recharges the water table. So these wells, or this style of well, there's no electricity, there's no power required. It's basically, you see the gentleman on the left with the yellow vest on, he's the horsepower. And there is a casing inside that galvanized tube with a piston, and it basically is like a plunger that goes down and goes underneath the water surface, and after it's underneath, you pull it back up and it pushes a small column of water out the spout. And so, but what it does is basically guarantees that the water coming into the vessels that these people are filling up will be clean. Less chance of contamination. But it is a fixed amount. When we talk about pumps and even water meters, we're going to talk about positive displacement. And that's what this is. Every plunger stroke goes down below the water table and then pulls back a fixed volume of water. Extremely reliable, very low maintenance required, and they're basically proof against contamination, things falling into the well, people, animals, that sort of thing, and allows for the best quality groundwater to come out of the water table. And again, doesn't require power. So in areas where power supplies are either non-existent or very sketchy and power may go out, there's always a source for supply. The big issue in these parts of Malawi is that the wells are quite far apart, and that the average time, typically it's women that are fetching water and filling up taking their needs, is an average of a 2-hour walk. That's a long way to go for a container of water. So it's a very markedly different type of setup, but it's a totally effective type of way of pulling water out of the system. So just wanted to show you, there's actually a spec. And if you want, and if you're interested at all, you know, this type of pump, this Africa Dev pump has been around for 30 years now, 35 years. And basically you can see the parts of it. You can actually look at the different specifications, human powered pump, average flow, 23.3 liters per minute at 10-minute intervals. So basically it's limited to the stroke on the actual arm, right? And you can actually here see an example of it being pulled. But you can actually order these and figure out there's a bunch of downloadables, figuring out who's got the material and where you can get them installed. So a lot of the actual installers will come out of South Africa, not Malawi or Tanzania. But there's a cross section. See if I can blow that up. And parts of the well that we're going to see a little later on are quite similar. And most important, at ground level, is a sanitary slab that prevents contamination in the well. The actual cross section, though, because they're mostly hand dug, you don't see this nice drilled casing like we saw on the video. This is hand dug, backfilled with material that allows water to move through down to the intake at the bottom. And there's the plunger. It's even tough to see on this, but you can see the plunger right there. And it basically moves down to the bottom of the casing and pulls it. And the foot valve, we'll talk about that actually, that'll be on the test. A foot valve basically prevents all of the water that's moved up towards the spout from spilling back down into the groundwater surrounding the casing. So sanitary seal, this is all bolted up. The casing comes up in through the galvanized. That's set into the cement, flanged into the cement, and then basically a couple of bolts to connect to the actual rod that pulls the pump rod that pulls the plunger up and down. So a very basic construction method, but that makes it durable and able to last in very difficult conditions. Here's an example, slightly different construction style, but same principle, but varying depths. And depending on the actual water table, the water table level, it may be drilled as opposed to hand dug. The ones that I was working on were more to do with hand dug wells. So this would replace that hand dug area. So you would, underneath that, would see a much broader casing. It wouldn't be a neat casing that was drilled into the ground, most likely, but it would have been installed, backfilled, and then the concrete pedestal is installed on top of that. So it's still a well, and it's still very functional, and the advantages, of course, are that there's no power requirements. Disadvantage, doesn't bring up a lot of water at each cycle, at each rotation of the handle, but it's reliable. And the most important thing for the communities where it's been installed is that it protects against contamination for the most part. I mean, obviously, after water has been pulled from the well and into the containers, there's a potential for contamination there, but the well supply itself is protected. And that's really what we want. It's the same with the casing on the video that the well driller was talking about, ensuring that no surface contaminants can enter the well. So just to recap, basically dug wells are looking at a casing that could be brick, could be steel, it could be concrete pipe, like a manhole stack, depending on the diameter that the well was dug, but it has to support the material that surrounds it. That one picture, that's pretty solid material here. May not be an issue, but in heavy rain, it could erode. So the goal is, once this is finished and whatever depth it's at, there will be bricks installed to support and protect the well, the actual well, from collapse. So basically, the casing may be the plastic style that we saw in the drilled well, but with a dug well, it could be all of the above. It could be brick, steel, concrete pipe, or other material. Disadvantages of a dug well, and this may show up on the exam, but basically they're not as reliable year-round, partly because they're so shallow. And if you have high variation in the depth of the water table, then you have a potential for the well actually to be dry at the time of year you need it most. So dug wells, that can be a concern. And in fact, that was why a lot of the communities where we worked and provided with grant money went to this style, because this style of pump can be, or well, pump can be drilled up to 20 meters, 6 meters, 20 feet, as opposed to 6 feet. And that gives it more chance that it will be able to be useful in the dry season, or when the water table's at its lowest. But the other concern about dug wells is the potential for pollution. And we're not talking about afterwards, we're talking about actually the water in the well itself can be contaminated, either by being open or from the movement of surface water running into the well itself. And that can be a problem. One of the, in fact, the biggest sort of tragedy in Canada, in Canadian history, that was reported was the Walkerton contamination event 20 years ago, actually almost 21 years ago, May 2000. And there were shallow wells were not dug wells, they were bored, but they were only about 6 meters deep. And the ground, surrounding ground around the well had not been properly supported the casing. And surface water, when there was heavy rain, the wells were in low places. And when there was heavy rain, it picked up material from the farms that surrounded the wells. Those farms were livestock farms. And, you know, cattle and sheep and pigs do a lot of pooping. So there was a lot of animal waste that was spread on the fields around the wells. Now, this is in Ontario, and they did have a Ministry of Environment that recorded all of the information about the wells, just like they do in BC. So they knew the depth, they knew the yield, how much water could be pulled. And these were for the city. They were a city of 5,000 people. So quite a bit of water was needed to be pulled from these wells. The only problem was that because of the fractured ground and the poor condition of the casing, when heavy rain happened, all of that waste material, so heavily laden with fecal coliform, E. coli, ran down alongside the casing, which is exactly what we don't want to happen, and contaminated the groundwater. So then the groundwater that was being pumped was already contaminated, basically by heavy rain and animal waste, which then resulted in half the town getting sick. 2,300 people got sick, 7 people died. And a lot of those individuals that were sick and recovered had health issues. E. coli is not very friendly to people's kidneys, liver, and basically organ function. And so a terrible incident that took place, and it took them a while to figure out where the problem was coming from. The wells were decommissioned. As a result, new wells were installed. A different agency actually took over running that utility because the operators of the system, actually, none of them had ever written a certification exam. They were grandfathered, so they didn't really understand how a water system should be run. And that resulted in, they didn't make the people sick. The wastewater contamination, fecal coliforms in the water made people sick. But their lack of understanding of how those wells really operated was a huge contributing factor to those people getting sick and dying. So no matter how the well is constructed, that's really so critical. Whatever agency is responsible for the development of the well, the installation of the well, testing the well so that we know what its capacity is, and then the long-term maintenance of the well. They need to be qualified at that work. Otherwise, potential for catastrophe. So bored wells, the first video that you saw from the Caribbean was actually a bored setup using a larger drill rig. The bit can actually be up to 1 meter in diameter, so much larger casing, but typically not going into bedrock. Bored wells, the key characteristics, up to approximately 30 meters in depth. And they, again, are very useful and versatile where water table is high. But they're typically not designed to penetrate bedrock. Their casing can also be concrete pipe. In fact, it's quite common to see small concrete sections being lowered down and stacked after the bore tool has been finished, has been removed. And then, because you don't want to collapse that material into what is eventually going to be the housing for the pump. So it's really important that that remain intact. Another concern, and in there, that picture, you can see quite a large diameter boring bit that is going to be lowered into the ground to create, I mean, there's the well driller to the side. So we're talking probably a 2-foot, 600 millimeter diameter bit. But because they are also quite shallow relative to a drilled well, seasonal variation is potential. If the water table is a variable. That is, it's not going to stay at the same level based on time of year. Never mind that anyone's using water, but time of year, that could be a risk factor. Also, greater chance of pollution from surface water. So dug wells, bored wells. We will talk a little bit about drilled wells in a minute. But just as a refresher, remember, our groundwater source, the aquifer, basically sits above the bedrock. It can be also trapped below the bedrock. But what we're looking at with a hand dug well in this cross section, if we were hand digging, we're really just digging out the topsoil and a little bit of clay so that we can get to that top water line. Once we have that, water can move underground into our well. And it may be through the natural ground, it may be through brick or concrete or plastic that we have drilled out. But the aquifer itself would be a lot closer to the surface. A bored well would move through the topsoil, the clay, into the sediment soil. And the same thing, allow for water to move through. But if we're going to go into groundwater below a bedrock, then we're talking about drilling a well, and we'll talk about that in a minute. But remember, the other piece that we talked about when we were looking at groundwater, and this really was coming into effect at this example of Walkerton, is that when water comes from the surface and percolates down through layers of material, it acts as a filter and removes potential microorganisms, pathogens, before it gets into the aquifer. But as in the case with Walkerton, if the surface water and precipitation doesn't get filtered out, you have potential for contaminants right in the groundwater. And at that case, we have a term for that, right? We have a concern that potential pathogens are getting into the groundwater. We call that groundwater under the direct influence, or GUDI, G-U-D-I. Groundwater under direct influence. Influence of what? Surface water. So that first video we looked at, water running across the ground, that's surface water. Rain hits the ground, or snow melts, runs across the ground, that's surface water. And if it can get into our aquifer and affect the composition, the characteristics of the groundwater, we have to then treat that groundwater like it's surface water. So what that really means is if you're a water system operator running a well system, and that well is affected by surface water, then the regulator will probably insist that you disinfect like you would a surface water supply. So instead of just collecting water from the surface and dosing with hypochlorite, you've had to go to all the expense of drilling a well, finding the well site, drilling the well, installing all the component parts. Now you have to treat it just like surface water because of the characteristics of the topography, the geology in that area. And that becomes important because otherwise you have the potential for serious contamination. All right, so I want to show you this other little thing. I can find it. Oh yeah, here it is. Okay. A little bit of the same. Okay. Just some animation on drilling out a bore well. And you can see basically a percussion style drill bit. Basically, the high impact is forcing its way through overburden into the material below the topsoil, down into the aquifer. And injecting water and air to take all of this material that it's broken up and remove it from the shaft. Otherwise, it would plug it up and wouldn't be able to move. So that's why you see material moving up to the surface all the time. So the drill bit itself is breaking up all of the material. The fractured rock is where the water will move, the groundwater will move through. And then the casing will be installed. And then a smaller head is installed inside the casing to finish the work in the actual bedrock formation. Until the actual percussion bit actually enters into the water table. All right. But you know, it doesn't always go well. Sometimes even the best plans go wrong. Let's take a look. So this well has already been drilled. The casing has been installed, but unfortunately the casing doesn't want to stay put. It's actually the water table, the force of the water inside the well, that is pushing this casing back up. So the well is actually pushing the casing right back up. So the water pressure is pushing the casing out. So all their work up to that point is basically ruined. So same principle, just didn't work too well. I like how the homeowner didn't want any part of it, but came back right at the wrong time. So it doesn't always go well. But basically the same principle is we're going to drill into the aquifer. We're going to set a casing, secure it, support the material around the well casing, and then protect that well from contamination. But sometimes we have to do it more than once. All right, so we talked about Grouting. So remember that the shallow wells, a hand dug well, like the ones we were looking just at in Africa, or the bored wells, are considered Grouting. So in other words, by default, in Canada and the United States, that if you are installing a well that's that shallow, they have to be inspected by a professional engineer, hydrologist, to ensure that the well is protected from surface runoff. Otherwise, it's automatically the person, the owner, the client, is going to have to treat that well as if it is surface water, which is an extra expense, right? And an extra whole set of maintenance that's required. But another good reason why the standards are set so that qualified professionals make that determination. And if they determine that no, even though it's a fairly shallow well, it has been installed correctly with a sanitary seal, that the surrounding geology of the aquifer is supported enough that we're not getting water down alongside the side of the casing or percolating into the ground in the vicinity of the well, then we can treat it truly as groundwater. Otherwise, that becomes the minimum requirement. So drilled wells, slightly different story. Typically gives us the flexibility of going much deeper. Also the same types of diameters, basically 0.15 to 1.4. So 6-inch all the way up to basically 4 to 5 feet, right? 60 inches can be drilled. Also extremely deep, 250 meters. So going through multiple layers of bedrock and rock formations in order to get into the aquifer. And one of the issues we talked about earlier last week about water sources in terms of diminishing and depleting aquifers is the deeper you go into a water supply, a groundwater supply, typically you're talking about an aquifer that will take much longer to recharge. So instead of something that recharges on a seasonal basis, dry summer, water table drops, winter, snow, rain, water table recovers. Meanwhile, people are still using it. When you have to go that deep, 250 meters, sometimes even deeper than that in California, they've got wells drilled over 1,000 feet. That's water that may take thousands of years to recover, to actually get back into that part of the aquifer. So those kinds of decisions, also regulated by local or county or state governments, really determine the viability, first of all, of the cost of the operation, but also what you might be paying for the water supply in its own right. So we see in irrigation areas in the United States that have suffered from long periods of drought, drilling deeper and deeper, now the state government is actually saying, no, it's too deep. It's too much impact on an aquifer that we're not going to recover from. The other feature is, of course, as we mentioned, you can drill through bedrock and you can line that steel pipe with steel casings typically. So it becomes a very permanent feature that allow you to start drawing water through the well. And really the two factors around dependability are the deeper the water, less susceptible to surface contamination. Not just because the soil layers provide more filtration, but it may be going through impenetrable layers that cap and protect the aquifer from any surface contamination. They are also then typically installed in aquifers where that depth of water table is consistent year over year over year. If it's an aquifer that's taken thousands of years to create, chances are taking water out for one season is not going to change that. Where the impacts have been over, say, 120 years in California is thousands of wells now, operating year round, that becomes a different issue. But the two main factors for drilled wells: deeper through bedrock and less susceptible to contamination, which is a critical factor. Because of that, less likely to be considered groundwater under direct influence, which means then once the construction is complete, you're looking at a maintenance program that doesn't necessarily require disinfection unless your state agency or local government requires it, but doesn't have the same requirement necessarily as if you were taking from surface water, from a creek, a stream, or a lake. So this is a piece to have a good grasp of for the exam, understanding the different parts of the well. And you can see the cross section. The casing extends from above the surface, so above ground, all the way down into the lowest portion of the drill, which is inside, obviously below the top layer of the water table. You can see, in fact, the water table is that differentiation between brown and light blue. That'll be the high space. And this representation is as if the pump is not running. So the water table's up here, the well is, and the pump are well below that. There's a screen that prevents material from small sediment and clay from being pulled up into the pump and clogging the pump and preventing the water from being discharged. But there's also a gravel pack, which is actually just in this immediate area of the well screen, and that's to prevent the smaller sediment from pushing through the screen. Because one of the long-term maintenance problems is that over years, that well screen may rust or oxidize and break, and then bigger particles can get through. And if that's the case, that could plug the pump. The pump itself sits above the screen and pulls water up through the discharge pipe. So the actual volume of water that's moving through the pump is actually shown in this much smaller diameter pipe. That is the pressurized water supply. And depending on the capacity, the pump might be extremely small, might only be a single horsepower doing 5 gallons per, or 2 gallons a minute, which means that you may not, when everyone's using water, have enough supply to pull it directly out of the well, in which case you would actually pump into a reservoir and fill that reservoir first, and then draw from that. So that the reservoir could be filled when people aren't using water or need water. It's just basically controlled through the adapter, and then the controls on the reservoir to turn the pump on at a certain volume in the reservoir when it's half full, say, and fill that so that it can be used at a later date or time. The grouting is basically the black line that you see. So the casing, and then the black line just beside that casing is where the grout would go. And that basically supports the casing against the original ground. And that hole, or that gap between the casing and original ground, is called the annular space. And that shows up on virtually every exam for level 1 and potentially half the exams for level 2. So recognize that the annular space, if you're looking down from above, there's the whole, the circle, the diameter of the casing, and then there's a slightly larger diameter for the original ground. That space in between is the annular space. And that is the space that is typically filled with grout. The well cap and the slab, sometimes it's called the slab, is part of that sanitary seal at the surface to prevent water from running down the casing and into the aquifer. And over here, just that little piece where it says open water, here you've got surface water, and water will, in the wet season, run underneath that creek and percolate into the water table. So you've actually got a water table high enough to exfiltrate, so water moves across the ground and actually into this channel, And then in the summertime, perhaps the water table drops so far, this actually strands and dries the creek out, which is quite common. So basically the main parts, remember the water table, remember casing, the sanitary seal, which prevents surface water from getting down, and then the various parts of the actual well itself. Sanitary seal prevents contamination, right, from entering the well casing. The slab, and it could be as sophisticated as a steel / reinforced concrete slab. I've seen wells that have been installed in parking lots where it's basically just an asphalt collar around it. But the sanitary seal would be in addition to the slab, so that in case the slab itself cracks, you've still got the sanitary seal to prevent contaminants from entering the casing. The casing can be, in case of a drilled well, typically steel. And that holds that, otherwise the well, the surrounding ground would collapse and then your pump wouldn't work. Remember, in a hand dug well, that can happen, right? There's no supporting material installed. It's just dug into the topsoil and overburden and through the supporting soil. Well, over time that can erode and fill up that well space. And then the grout itself is the material that is that mixture of cement and water and sand that's pumped down against the casing, and that helps support the casing, but also when it sets up, it actually prevents water from building up and moving down along it. The annulus, we talked about that annular space, the space between the drilled hole and the casing. The well screen is where we're actually drawing water from. So the suction of the pump, there's a well screen around that to prevent particles and any material from getting through. Gravel packing basically is clean washed gravel that's installed basically below the casing and around that screen to also prevent material from moving through. We want that water as clean as possible from a capacity issue, right? If we have sand and sediment getting through, our pump isn't going to work. And the Pinless Adapter basically connects the outside plumbing line on the discharge line right where it leaves the casing. It could be 3 feet below grade, 5 feet, depending on the actual well itself. So as we talked about, when a pump is then installed in a well and that's turned on, the water table will be drawn down. And we've sometimes called that a cone or a circle of influence. The static level or static water table is that highest level that the water table reaches before a pump is turned on, right? And we measure it typically from the top ground. You had some math questions on that, right? Top ground down to the water table. Meanwhile, the pumping level is the lowest level the water table reaches. Pump has been turned on, 20 minutes, 30 minutes, 40 minutes, if it's running that long. When that circle, that cone of influence draws down, that lower level is the pumping level. And the difference between the top water table and the drawdown is, the pumping level and the water table is drawdown. And we can actually measure that. We can actually measure it by calculating the flow as it leaves the pump, or measure it as it enters into a reservoir or a vessel that is graduated, and we can actually see the volume. Or we can calculate that based on the pump information and the time it's running. So we've seen this before, original water table below grade. So this could be 4 meters. Use meters. 4 meters below grade is the original water table, and that's with the pump not running. Once the pump starts turning on and it starts moving water, discharging water through the well, the cone of depression brings down the drawdown, and then that lower level, this may be the maximum, but let's just use the line that they've drawn here. This becomes the pumping level. The drawdown is the difference. So if this is 4 meters below grade, the pumping level is 24 meters. The drawdown would be the difference, so 20 meters. So 4 meters plus 20 meters of drawdown is a pumping level of 24 meters. That's basically how we're calculating the yield, the actual amount of water that we move through. So the cone of depression is that radius of the pumping level, right? How far, and when we're looking at multiple wells that have been installed within a watershed, one of the things we're concerned about is overlapping circles or cones of depression, circles radius of influence, because then that means that one well is interfering with the actual drawdown of the other. So how do we know that? Well, we calculate the yield, the rate of water withdrawal, right, that a well can supply over a long period of time. And that may be varying based on time of year and also the regulations of the local regulator. The specific capacity is yield per unit of drawdown. So it's a little different. So the well yield is the rate of water withdrawn. The specific capacity is the measure of the yield per unit. So we track the specific capacity of well over time, just to note how is the well doing over time, because we install it in 2010, 2012, we're looking at that numbers, we record that data and see, is it still capable? Pump is running for an hour, but it's only 20 liters per minute instead of 40 liters per minute. All right, that may tell us we have to do some maintenance on the pump itself. So this becomes important information to log, and most well houses, you'll see a logbook that will be kept, or actually if it's digital now with a pump control panel, that'll be tracked historically, so that we can see that, first of all, is the aquifer still capable of sustaining the well based on what the customer needs, or customers, and what is the effect of time on our maintenance programs. Do we have to replace the well? Do we have to clean the screen at the bottom of the well casing? What do we need to do? And that we basically use the numbers through the pumping rates in terms of yield and capacity, specific capacity, to determine how our maintenance works. The other thing about, of course, protecting the water from contamination is it's not just bacteriological contamination, but surrounding land use, right? Just as an example, industrial land discharge, road salt. In this part of the world, you probably don't use salt on your roads because you don't get ice necessarily. But in this part of the world, that becomes a real problem. And the federal government has insisted that cities now have a road salt management plan, because that road salt that melts the ice and snow then washes into surface water supplies and can percolate into groundwater as well. Landfill can leachate, so material decomposing in a landfill can actually move into an aquifer and create problems. Very heavy corrosive materials, but also toxic materials. Pesticide use, agricultural use, right? So herbicides, fertilizers, all of that material can be put on the ground. It eventually will make it into groundwater. So the Walkerton case was an example of manure being spread in a field near a well. And that created that, when you combine that application or that activity with groundwater under direct influence of surface water, then you have that potential for contamination. So it becomes really critical about managing the actual condition of the well, but also being aware of what is happening in the surrounding watershed. In this part of the world, there are a couple of very contentious developments happening because they're using some very low-lying land to dump excavated material. Could also be contaminated with hydrocarbons and petroleum products, that sort of thing. Well, that'll percolate into groundwater, and the neighbors that draw water from the aquifer are concerned that it may not be today, but eventually that potential for percolation through into groundwater could be a problem. Not so much with bacteria, but with chemicals, toxic chemicals. So we have to be very concerned and aware of what that potential is. So obviously agricultural runoff contains materials that we don't want in our drinking water. And contaminants can move through the aquifer. Once they have come through the surface and then into permeable soil and sediment and gravels, then that can move through the aquifer. The other problem is if it's not been properly constructed, or the well has not been maintained many years after it was installed, then we have the potential for contaminants directly entering the well. The example of Walkerton was these wells were almost 40 years old at the time of the incident. And you could see some problems with how they had been maintained over their life. So that becomes really critical, is that not only are they standards that well operators need to follow at the installation time, but in the maintenance over time, those standards need to be maintained. And whether it's local governments or regional governments, getting that information so that they can inspect and make sure that they're operating correctly. Locating a well in the first place ensures that that's a safe distance from potential sources of contaminants. That video that you watched basically showed the fellow with the witching rods. Okay, there's water here. There wasn't really a discussion about what is the land being used for surrounding that potential well location. But that becomes a real critical factor to be considered when siting a well. So what's really critical for well maintenance is, one, it's under the, it's been installed under the guise of oversight of qualified professionals. So it's in the right place and it's been installed correctly, but then the records need to be maintained. That document I showed you earlier from the BC government says these are how you do your tests on the wells and then do inspections. Those records need to be maintained and kept. It's no different than working in a pump station or a pressure regulating chamber and maintaining records of what's the upstream and downstream pressure, when was the last time that the globe valve was taken apart and serviced, or the diaphragm replaced, what's the maintenance cycle on the pilot valves and the associated plumbing. Wells are exactly the same. Keep good records that show how much water is being pulled out of the well over time, so that you know what's happening with the aquifer, but also what maintenance that you may need to do. And the more corrosive the groundwater or heavy mineral content in the groundwater, the pumping records will tell you that screen is getting plugged up. Very hard water, lots of scale, calcium carbonate, that sort of thing. The well screen may need actually to be blown out, so pump taken out, and push water or air back through the screen to blow incrustations off with high velocity equipment, or actually with some chemicals to allow for the particulates to be dissolved. And how you know that you need to do that is through the record keeping, right? The more records you have about what the pump is delivering into either a reservoir or directly into the water system, the better you can time any maintenance that you may need. So the other thing that happens too, depending on the location of the well, the depth of the well, and the strata surrounding the well, is that the water quality can change. It's not just the actual condition of the strata, but the water actually moving through the water table. And that could be because of other activities around the well. But water quality problems or maintenance problems basically include the clogging of the screen, could be the actual disintegration. I mean, these are very thin in some cases, thin, almost microfoil type screens on the small diameter wells, kind of like on the electric shavers, those very small screens. They can collapse, they can tear. So then that allows material to be pulled in through the pump that can damage the pump. And so that means the pump has to be pulled, taken out of service, and either repaired or replaced. The other problem that could happen is the pumping times may be extended so that you're running more hydro. Your electrical bill goes up because the pump either has starting to fail, maybe an impeller or a seal inside the pump is starting to leak, so you're not getting the efficiency of the pump itself. All right, so a couple of review questions. We basically covered off what we need for level 1 and really level 2 for around wells. So if the static water level is 45 meters below the surface, the pump turns on, and then we get 65 meters. What is the drawdown? So we just did this, basically 45 meters, 65 meters. The drawdown is the difference between them, right? So 20 meters. Always remember that the pumping level, if they're asking you these math questions on a cert exam, the pumping level will be the biggest number. The static water level will be the smallest number, and the drawdown is the difference, right? What is the primary purpose of well grout? So, protect the well casing from corrosion? Probably not. Typically steel, we're talking about a drilled well here. Seal off poor quality aquifers. Well, if we know the water is poor quality in an aquifer, we're probably not installing the well in the first place. Prevent contamination from surface water, or prevent damage to the well casing. So the best answer there is prevent water from surface contaminating. So in other words, by grouting, supporting the casing, it actually stops surface water from moving through. And the reason that's the best answer, preventing damage to the well casing, it supports the well casing, but doesn't necessarily prevent damage. A steel casing doesn't need a bit of sand and cement to prevent damage to it. The steel is much stronger. But it does support the casing. So if they had reworded that last choice, that may have been a better option. So if the pumping water level is 53.5 and the drawdown is 45.8, so pumping level is the lowest, the biggest number. We already know we're looking for the smallest number. Where's the water table? Okay, 12. All right, 12.5 meters. Right, we subtract 45 from 53, so that's not correct. 7.7, that's the arrows in the wrong spot. The static level is 122 meters. After the pump runs for 45 minutes, the level reaches 156. What's the drawdown? So in a level 1 exam, you're not going to have to do any volume calculation. This is strictly addition subtraction, right? There may be, and it won't be at level 2, it would be level 3. You might actually have to do a volume calculation, but they have to give you more information than that anyway. But really, we're looking at static level of 122, pumping level of 156, the difference between them, 34 meters. So that's the level of the math required around the wells. The other feature of the wells is being comfortable with the parts of the well, recognizing the difference between them. Okay, that's the unit. Let's bring up the math from last week. So let's just share that. Let's see. Okay. I will send you these through, or get Ignatius to send you the answers from last week, as well as the questions from this week. For some reason, the chat doesn't let me send files from my computer, and also the PDF of the today's presentation. So this is what we handed out last week. It's been a long week. Disinfection equals destruction of pathogens plus inactivation. So the total disinfection process doesn't require killing everything, just preventing the bad bugs from reproducing. So that keyword there is inactivation. What does the presence of total coliforms in drinking water indicate? Not guaranteed contamination, but possible contamination. Because we're looking at the key word here in the question is total. Where in the distribution system should samples be collected? At representative points in the system. In other words, they need to be where you think there are weak spots in the system, or where there are lots of users. Okay, a well question. Static 25, pumping 47, the difference between the two hopefully is 22. Yes, 22 and 25 is 47. In a well supply, the static level, pumping water level plus the drawdown equals, this pumping levels, static water level plus drawdown equals pumping level. We just reviewed Grouting again, groundwater under direct influence. The units that turbidity is measured in. Remember, turbidity is actually a measure of water's ability, the particles there, to reflect light. So methylometric turbidity units. The lower the number, the better. Two examples of primary water storage. So a lake or a reservoir. Could be a stream. What is the sodium thiosulfate in a bacteriological sample bottle used for? It neutralizes the chlorine, right? If you want to take bug test and you have chlorine in the water, that will alter the actual result of the sample. What is an aquifer? An aquifer is the sand that holds the water. So it's the ground, right? We're not talking about empty chasms full of water underground. We're talking about soil that allows water to move between the spaces, right? Okay, so those are the questions. I'll get those sent to you as well. Let's see. These are the questions that you'll be getting through Ignatius at the end of this session. 10 questions all about wells and the types of wells that are in this that were in the slideshow today. Next week, we will be looking at a little bit of water quality, a little bit of bug testing, and then we move on to actual water system maintenance. And we're going to focus on areas, not just for the exam, but they tend to overlap. The types of processes that you have to do in your system to ensure that you have enough water and that it's safe to drink. So things like hydrant maintenance, valve maintenance and inspection, backflow prevention, that sort of thing. So same time next week, Wednesday at 3 p.m. your time, but we're done for the day. So thank you very much.
Thank you very much, Mike. That was a very enlightening session, particularly for many of us who have not had the experience of drilling. So I think that was very useful, and perhaps to bring it into perspective, those who would still have to write aspects of drilling in or to have the knowledge for the examination, and for maybe for the future if they're going to do it in their country. So that's very good.
All right, I'll send you the files, Ignatius, so you can pass them on to PDF
Yes.
to Word documents.
Thank you very much. And just to let you know, those of you who are following this session, we have at 5 p.m. we have a webinar. If you so wish, you can join us. If you don't have the link, you could shoot me an email and I will forward that to you promptly. Have a good afternoon, everyone.
Thank you. Yeah. Be safe, everyone. See you next week.